Welcome back to our latest technical explainer. Today we're doing a deep dive into decoding cow manure wastewater. Specifically, we're logically breaking down the treatment flows and strict effluent standards when using Archaea water. Look, if you're an engineer or a system designer tuning in, you already know we can't rely on abstract theory here. We're going to map out the concrete structural logic you absolutely need to turn a massive environmental liability into a tangible agricultural asset. So let's get right into it.
Here's our roadmap for today. We'll start with the overall flow and basic design, then look at target discharge standards. From there, we'll hit the liquid phase, specifically Archaea phosphorus recovery, and the solid phase, covering composting and fertilizer. Finally, we'll wrap up with the realities of limits and complex treatment, ending on verification design and legal compliance. All right, Section 1, overall flow and basic design.
Okay, to build a compliant system, we first have to map out the macro philosophy, right? How exactly does waste become a resource? Well, looking at this sequence, the fundamental premise of our treatment flow is immediate separation. You take the raw cow manure solution, run it straight through solid-liquid separation, and boom, you send the water and the solids to completely different exits. The liquid phase gets diverted for phosphorus removal, and the solid phase heads straight to composting. This dual pathway approach, that is the absolute bedrock of your engineering design. And here's the crucial takeaway. It's almost a golden rule. Phosphorus doesn't just disappear. It concentrates in the solids. The cleaner the water, the richer the fertilizer. As engineers, you know we aren't magicians deleting pollutants from the universe. We're actively and deliberately converting them into a concentrated agricultural resource. It's a beautifully closed-loop system where solving your liquid pollution problem directly creates the value of your solid byproduct. Moving on to Section 2, target discharge standards. Let's look at the legal targets you absolutely have to hit. 16. That right there is the magic number. 16 milligrams per liter is the Uniform National Effluent Standard for total phosphorus. If you're designing a system that discharges into public waterways, you need to have this number burned into your brain because it literally dictates the success or failure of your entire liquid phase treatment protocol. But, of course, engineering compliance is never just a flat, simple number, is it? The daily average target is actually even tighter, sitting at just 8 milligrams per liter. Now, these statutory standards kick in if your facility discharges an average of more than 50 cubic meters a day, especially into designated lakes, seas, or the waterways flowing into them. There are a few nuances, though. Pig farms, for instance, have a provisional standard of 22 milligrams per liter until September 2028, but cow and horse operations, they've already moved to the general standards. So before you finalize any schematic, you've got to verify your facility's exact discharge volume and location. Plus, always double-check for local municipal add-on standards. They can sneak up on you. Okay, Section 3, liquid phase, Archaea phosphorus recovery. Let's get into the biochemistry. This is where it gets really fascinating. We're shifting a massive chemical headache into a tangible asset. MAP stands for magnesium ammonium phosphate. In the liquid phase, Archaea microbes go to work altering the pH, ammonia, and magnesium levels. This precise biological shift causes the dissolved phosphorus to actually precipitate out as MAP, making it fully recoverable as a high-value fertilizer. It's like a biochemical magic trick, but it's pure science. So the Archaea water is actually fighting a two-front war to aggressively drop those dissolved phosphates in your effluent. On one side, you have cellular absorption. This is where the Archaea literally incorporate the dissolved phosphorus directly into their own microbial cells as polyphosphates. On the flip side, we have the MAP precipitation we just talked about, altering the liquid's chemistry so the phosphorus crystallizes and just settles out. Both of these mechanisms work in tandem to strip the liquid stream of regulated pollutants. Which brings us to Section 4, solid phase, composting and fertilizer. Let's see what happens to all that stuff we just pulled out. This right here perfectly illustrates the circular economy, what's often called the medical food agriculture loop. That sludge you just separated out of the water, it's routed here to receive all that concentrated, precipitated phosphorus. In the solid phase, the Archaea actually promote rapid fermentation. This is a huge deal because it significantly reduces facility odor, which, let's face it, is a massive operational win. But more importantly, it mineralizes organic phosphorus, making it super available to plants. The end result? You've created a high-value, slow-release MAP fertilizer. You've taken a strict legal liability and engineered it into a highly marketable asset.
All right, time for Section 5, limits and required complex treatment. We need to ground ourselves in some harsh engineering realities here. Because here is the ultimate reality check, folks. Raw cow manure slurry often contains hundreds of milligrams per liter of phosphorus. As amazing as biological systems are, Archaea water alone cannot magically drop those levels all the way down to that strict 16 milligrams per liter standard. Relying on just one single microbial additive to close that massive mathematical gap, it's technically impossible and frankly mathematically unsound. You absolutely have to design a complete, integrated system.
Therefore, you've got to treat Archaea water as just one highly efficient element within a mandatory multi-step treatment train to guarantee safe discharge. There are no shortcuts here. A robust, fully compliant system requires initial solid-liquid separation right off the bat, followed by your biological treatment phase using the Archaea. From there, you have to move into coagulation and crystallization for even more phosphorus removal. And finally, run it through a rigorous polishing phase before a single drop of water leaves that facility.
And let's be real, you can't afford to get tunnel vision on just phosphorus. To stay fully compliant, your system has to continuously monitor and treat for biochemical oxygen demand, chemical oxygen demand, suspended solids, and total nitrogen levels. The law demands multi-metric water quality improvement, so your overarching engineering design has to tackle all of these parameters concurrently. It's a complex puzzle, but that's the job.
Finally, Section 6, Verification Design and Legal Compliance, because all this engineering means nothing if the paperwork isn't bulletproof.
Your facility's data reporting has to be rock solid. For example, in Japan, strict compliance with the Act Against Unjustifiable Premiums and Misleading Representations is an absolute requirement when reporting your results. You can't just go out there and claim impossible biological miracles. Your marketing and your reporting must be rooted entirely in your engineered, measured data, or you're risking some very severe legal penalties.
Just look at the stark difference in terminology here. Safe engineering language sounds like reduced total phosphorus by X% based on measured values. High-risk dangerous language uses flashy terms like purified or eliminated. Claiming the water is completely purified creates a huge, legally dangerous misunderstanding of the actual science. It implies the phosphorus just vanished into thin air rather than being actively transferred to the solid phase. Always, always let your measured data do the talking.
So as you move forward to design a system that truly turns pollution into profit, you've got a crucial choice to make. Will you draft a comprehensive process flow diagram first, or are you going to start by building your effect verification protocol? Which foundational document will you create today to guarantee both your engineering success and your strict legal compliance? Thanks for joining me on this explainer. I hope this logical breakdown really aids in your future designs. Catch you next time.